Okay, so our next speaker is Michael Sammler from ETH Zürich. We'll be talking about separation logic.
Very so.
Yeah, 1 moment.
Have you tried plugging it out and plugging it back in?
No, I just need to do like fancies. Almost. I think what I want to do. Yes. Okay.
Still very pink.
How do I? Oh yeah. Do people like pink? Yeah, I can make it less pink. Okay. That's pink now. Okay. Yeah. Thanks everyone for coming. I'm Michael, and I would like to tell you a bit about recent work on formal foundations for translational separation logic verifiers, and this is joint work with Thibaut, Gaurav, Alex, and Peter. So let me first explain what I mean with translational verifiers. So first let's talk about how do verifiers work in general. Well, let's say we have a program and we have a specification, and then when we have a verifier where we give the program and the specification to the verifier, and then the verifier either says, yes, this is a correct program, or no, this is not a correct program. And yes, and translational verifiers are now a specific way of building such verifiers, where we split the verification process into 2 steps. So first, we take the program, which we also call the front-end program, and first translate it to an intermediate verification language, also called IVL. And then we use a backend verifier to verify this IVL program. And then this backend verifier tells us, either this program is correct or the program is not correct. An example of such an IVL is, for example, the Boogie intermediate verification language. And we're going to see some more examples later. So what makes the use of translational verifiers interesting is that we can, with one IVL, we can support multiple front-end languages. For example, we can have front-end for Rust, where we translate a Rust program and a specification to the IVL, or we can have a front-end for Go and translate a Go program to the IVL, or maybe more languages. And then we can have multiple different backend verifiers. For example, we can have a backend verifier based on symbolic execution to verify IVL programs, or one based on verification condition generations, or many different variants, or like other kinds of backends. And thanks to the use of the IVL, we can freely combine these different front-end languages and these different backends, which is nice because, for example, different backends might have different performance characteristics or being good at verifying different kinds of programs. And in this talk, I'm going to focus on separation logic-based translational verifiers. In particular, so examples of this are, for example, Viper, Chilean, or Verifast, and these leverage separation logic to allow modular verification of complex heap manipulating programs. So to make this all a bit more concrete, let me now show how we can encode a simple program into an IVL. So let's say we have here a front-end language. Let's assume it's just some standard CSL. And here in the front-end language, let's say we manipulate these point objects, which are just objects with fields x and y. And what this code does is it allocates a new point object q and then does some parallel composition of 2 pieces of code. The exact code doesn't matter so much, and then frees the point p in the end. Okay, before we can encode this code, we also first need to give a specification to this code. And here we say, okay, we have a precondition. We assume we get ownership of p.x and p.y. And in the post condition, we obtain ownership of q.x and q.y, and the values have they point to the same value, to the value of v. And also, as standard is in CSL, we also need to write down specifications for the pre and post condition of the two branches of the parallel composition, as you usually have with the parallel composition rule in CSL. And here, okay, we have this P1, P2, Q1, Q2. That doesn't really matter too much, or really not at all what they are. They're just unnecessary to make this proof work. But once we have now this program with the specification, we can now think about how can we encode this program into an IVL. And for this, we first encode the precondition. And to encode the precondition, we use an inhale statement in the IVL, or in very fast, this is also called produce. And what this inhale statement does is it adds resources to the initially empty state of the verification. So here and this encodes the precondition. So we're just adding this p.x and p.y to the state, modeling the precondition. The next step, we encode the new point construct. We do this by this havoc and entail statement. And this havoc statement is a non-deterministic assignment, which models the fact that this new point xy, this allocates a new object, so we don't know what the pointer is. So we say it gets this q gets some non-deterministically chosen value, and then we inhale the permission for the fields of q, so the pointer for q.x and q.y. And this encodes the standard separation logic rule for such a new statement, where we get in the post condition also ownership of q.x and q.y. Then, okay, we can also encode the parallel composition, which we skip for the moment. And then we come to the free statement, where we free p. And to model this free operation, we use the exhale statement of IVL, or also called consume, for example, in Verifiers. What this exhale statement does is it checks that certain the specified resources are in the state, and then we remove them from the state, which models what a free does. So we check that we have actually permission to p.x and p.y, so it has not been deallocated before, and then it removes them, so like modeling the deallocation. And this models also the standard rule for separation logic rule for freeing a pointer, where you give this in the precondition, and then you don't get anything back. And then finally, we also need to check the post condition that q.x and q.y both point to v, and again we can use model this using the exhale statement. So this shows the basics of how we can encode like some programs into the IVL, and how we can you have these like inhale, havoc, and exhale statements to manipulate the separation logic state in the IVL. So in this talk, I'm now going to focus on, so we've seen the picture of how the verification works. In this talk, we're going to focus on the other direction of this picture, which is how do we know that this is actually sound? In particular, what we get, like if we run this verification, at the end we get that the backend says, yes, this is a correct program. But this is not what we actually want in the end. What we actually want is we want to know that our front-end program satisfies the specification, usually according to the operational semantics of the front-end language. So this talk is about how can we prove the soundness of such an IVL-based verification approach, where we can transform a result that we have a successful verification in the backend to a statement about the program that the front-end program is correct. And the first step to do this is relatively straightforward. So, which is that, like usually these front-end programs come with a separation logic. For example, for this simple CSL program, you can have a standard CSL separation logic, and then these separation logic has a standard soundness proof. Or if we can obtain a triple in the separation logic, we know that the program is correct according to the operational semantics of the language. But now the interesting part is the second part, where how can we, from the fact that the backend reports that the program is correct, obtain a proof inside the front-end program logic. And this is what I'm going to focus on in this talk. And in particular, the contribution of this work is a general framework for proving the soundness of translational verifiers. Kind of answering this, a framework for answering this question here, how you can construct a proof for the front-end program and connect it to the backend. The first step of this proof is maybe relatively obvious. We're going from the backend to the frontend, and like if you look at the verification, this goes via the IVL program. All right. As I also forgot to say, so like in this work we have this general framework, but we also instantiated it to the Viper verifier, and I will come back to this in the end of the talk. But yeah, so when we do the verification, we go via the IVL program. So for the soundness proof, we're going to leverage the fact that we have an IVL program between the backend and the front end. So we're going first saying that the backend reports a correct verification. We're going to transform that into a fact that the IVL program is correct, and then from that go to construct a proof in the program logic of the front end. But there's still quite a few open questions. So first, what does it mean for the IVL program to be correct? Or like, how can we formally model these IVL programs? Second, we need to see how can we connect these IVL programs to the backends. In particular, there might be many different backends with different characteristics that we want to connect to. And finally, how can we obtain a proof in the front-end program logic from the correctness of the IVL program? And we're going to talk about these 3 points in turn, first starting by what does it mean for an IVL program to be correct. So first, before we can actually answer this question, let me briefly introduce how we model the IVL in this work. In particular, we introduce a language which we call core IVL, which models the core constructs of an IVL-based verification tool. Particularly, we have for example, an inhale statement in this language for adding resources, as we've seen before. And these resources, this A is an assertion over a generalized notion of separation algebra. So this core IVL language is generic in the notion of separation algebra, or separation logic that it is instantiated with. And this is part of this, this being a generic framework. Second, we also have a notion of exhale for removing resources. We have a have-out statement for non-deterministic assignment. There are a bunch of other statements, like standard statements. And then there's also like a custom statement where you can add like a statement special for the IVL. For example, in the Viper instantiation, we use this for field assignment. So now the question is, okay, now we have this core IVL language, we have the syntax, but what semantics do we want for this core IVL language? And, well, what do we want from the semantics? First, we want to connect this semantics, or like this core IVL language, to the separation logics of the front end. And to do this, we ideally want to have an axiomatic semantics, so like a separation logic for core IVL, so that it's easy connect the separation logic of core IVL to the separation logic of the front ends. However, we also want to connect the core IVL to the more to the operational automation used by the backends. And for this, it's really good to have an operational interpretation of core IVL or standard operational semantics, because these programs, the backends usually reason about these IVL programs in a more operational style. So the question is now, which of these semantics, how should we define the semantics of core IVL? And this is where one of the key ideas of this work comes in, which is why not both semantics? And in particular, this is what we do in this work. So we give these both an operational semantics and an axiomatic semantics to core IVL, and we use the operational semantics to connect to the backends, and we use the axiomatic semantics to connect to the front ends. And these two semantics are linked with what I call a completeness theorem. So which says that if an IVL program is correct with regard to the operational semantics, then we can obtain a proof in the separation logic for co-IVL. And this direction of this theorem is maybe a bit surprising, because usually when you have a program semantics and a separation logic, usually you have a theorem which says, like, if you have a logic specification, then the program is correct with regard to the operational semantics, which is usually called like a soundness or adequacy theorem. But here, due to the way our setup works, because we obtain the proof from the backend, we need the other direction of this theorem. And also, like, there's some non-standard things in how the separation logic is set up, and there are people interested. I'm happy to chat about that also later. Yes, but this is the first part. Also, like, I'm also happy to take questions at any point if people have questions. If not, yeah, yes?
I do, but it's previous slide on the syntax of your language.
Yep.
Excel and Inhale as separate things. Verifast and Gillian do not expose Excel and Inhale as statements in the language, but you have function call basically, and I'm going to be lost about Inhale as example. The production part of the post-condition is directly linked to the precondition because of unification and what you've learned. And that's not a problem with IDF, but in separation logic you're going to have that problem. And do you know how you would model this in your framework?
I think you can encode that, like if you have sufficient quantifiers, you can encode that. But
what if I don't want quantifiers?
Yeah, if you don't want quantifiers, yeah. So we've looked at like encoding using Inhale and Excel, but more for less a dynamic frame style. I think. Yeah, I think we would. Yeah, would be interesting to talk about this maybe offline. How one could encode this, like pipeline.
Back to that question. So this is specific about the implicit dynamic frames variant of separation logic.
No, well, so this is the part here where this language is generic over generalized version of separation algebra. So basically, when you can instantiate core IVL. You can pick a PCM for defining the separation logic, and like you can use that to put like a standard PCM for getting separation logic. But it's also generalized that you can, like the generalized here means that the notion of separation algebra is extended, that you can also instantiate it in a way that you get implicit dynamic frames, where you have like unstable assertions. But like, for example, if you want to instantiate it with the separation logic, you just say all your assertions are stable. Yeah?
I'm actually a little confused about why you want this operational view of things. In my mind, I have an IVL like Boogie or something. And in Boogie, the verification result is directly in terms of the OR triples. And a OR logic for Boogie, not in terms of an operational semantic. You can give one, but I think Boogie is effectively reasoning in the semantic.
So the backends that we connect to is on the one hand a symbolic execution backend, which just like linearly goes over the program, has its own symbolic state, and then if you have the operational view, you can just directly relate your concrete state of the IVL program with the symbolic state. So that works out quite well. And like the verification condition generation backend, we connect to the one by Gaurav, which was presented at PLDI this year, which is stated also as an operational semantics over also like a state with like total heaps. So the backends we connect to are more in this operational style. It would be interesting to see like if you connect with like another formalization of backends, one in the form of OR triples, maybe one could also directly connect to the semantics, but we haven't tried that. Yeah.
My postdoc, Steven Goikel, had a paper at ICFP 22 where he made a sort of semantics to VPL style primitives as a predicate transform. So I was wondering if that's also an alternative.
No, so I'm not familiar with this paper, and like we built on the as I said, we built on like the formalization of like kind of the boogie backend of Viper by Gorav, which is in this operational style. We've not, I don't know, yeah, not looked into directly using predicate transfer, but would be interesting to look at that and maybe chat afterwards. Yeah. Okay, then let's continue. Let's now look at the second part of how we can connect our IVL program to the backends. And here let's just say, okay, like two standard algorithms for a verifier are symbolic execution or verification condition generation. And I just want to highlight that these are two very different verification algorithms. For example, symbolic execution is usually some algorithm which goes over the program and manipulates like a symbolic heap represented, for example, as a list of heap chunks, whereas verification condition generation encodes the program to a formula, and in the case of Viper, this is like coded using a total heap semantics. And then even gets even worse in the sense that we don't just have two backends, but they are then often very like different variants of these backends, which have different heuristics, and these backends might also change and evolve over time. And connecting to these backends, so there are quite a few challenges. So we first need to formally model these different backends or prove these backends sound. But the key challenge that I want to focus here on the talk is that we want to have one semantics for core IVL, but which can model and connect potentially to all these different backends with different heuristics and different verification strategies. Yeah, so let me illustrate this challenge a bit more on an example of exhaling wildcards, which is an example of an operation where different backends have different heuristics. And there are like many more examples where different backends use different heuristics, like for example for handling magic wands or disjunctions. I'm just using wildcards here because it's relatively straightforward to explain. So to explain it, I first also need to introduce in like fractional permission. So in separation logic, usually you don't just have either full permission or no permission, but you can also have a fractional permission between like 0 and 1, and then inhale and exhale any fraction of this. And here we have a program which inhales first like full permission to p.x, and then exhales a wildcard permission to p.x, where the wildcard means it's an arbitrary amount of permission. And then afterwards it exhales 1/2 permission of p.x. Now the question is, according to the semantics of core IVL, so should this last exhale succeed or not? And this is not an easy question to answer, because this really depends on the heuristics used by the different backends. Let's say we have one backend which says when there's a wildcard permission, I just halve the amount of permissions. And if you do this, then this program would successfully verify, because you would have half a permission left for the last exhale. Or you could have a second backend which, when there's a wildcard, which says, okay, it removes all permission except an epsilon amount. And these different backend, and then the verification would fail. And this backend have these different kinds of choices for exactly how they implement this. And now the challenge is, how can we support both of these backends using the same IVL semantics? And this is where the next key idea comes in, which is that we over-approximate over the different choices that the backends can do by using angelic, non-deterministic or angelic choice. And this angelic choice allows the backend to pick the amount of permission for the wildcard. So let me illustrate this a bit more clearly, maybe. So probably most of you are familiar with the standard form of non-determinism, also called demonic choice, which is, for example, exposed by the havoc statement. So if you have the program where we havoc x and then want to prove that x is equal to 1, this should always fail. Like, we shouldn't be able to prove that x is equal to 1 because it might be some arbitrary other value. So this non-deterministic choice by the havoc statement is really demonic. The backend has to handle all possible choices of this havoc statement. In contrast, for angelic choice, for example, for this wildcard example we just saw, here we want to allow both outcomes, as we've seen on the previous slide. And this means we want to use the dual form of non-determinism, angelic non-determinism, which allows the backend to choose these different, like the amount of permission to remove on this exhale statement. And this is really, this use of angelic choice really allows our IVL semantics to capture different verification strategies by different backends. The way we encode this in our semantics is that instead of having an operational semantic which steps to a single state, our operational semantics steps from one state to a set of states. And with this, we can model both angelic and demonic choice. And with this, we can then connect to different verification algorithms. Yeah. Sasha?
Yeah. Can you say how this is different from the approach that Featherweight very fast had? But they also had this angelic and demonic non-determinism calculus to model precisely consumption and production. Do you know how different your approach is?
Yeah, I think the way I understand very fast this production and consumption is to model one specific verification algorithm, and what it does there, and I think it also has no non-trivial angelic choice, is my understanding. It only has empty angelic choice.
In the Featherweight very fast semantics, the one that was done in COP, the concrete semantics done in COP, to model very fast.
Yeah.
You said it didn't have non-trivial angelic.
Yes, I think so. And and I think there it's like more for describing one concrete symbolic execution, but here we use this as just a general specification device for for this IVL and then the different backends, like for over approximating over two different backends. Yeah.
Something very new. Thank you.
Yeah.
And this idea of angelic choice has a history. So
Yeah. So like angelic choice, that's not making clear. This is not like the first use of angelic choice. Like angelic choice is quite widely used. For example, used for specifying programs or for like linking with different programs. And we use it here concretely for modeling an IVL that over approximates over different backend verification algorithms.
The original idea was CCR. In this like operationally capturing different kind of behavior in your
Okay. Yeah. Then now let's look at the last part of how can we connect the axiomatic semantics for co-IVL to the front ends. And for this, let's again look at some parallel composition, some program with parallel composition in the front end language. First, let's see how this is encoded to the to the IVL. So to encode this parallel composition, we encoded it three different IVL programs. First one, large IVL program, which checks the main code of the program. So it checks, it first inhales the precondition, then it has the encoding of C0, then it checks the preconditions of the parallel composition, assumes the postcondition of the parallel composition, and then checks C3 in the end, and then the two branches of the parallel composition get encoded as separate IVL programs. And when we have these program, like this IVL program, we can then give this to the backend, and let's say, okay, the backends verify this, and we obtain an axiomatic semantics proof for our core IVL. We can then, use this proof to obtain the separation logic triples for our front end CSL. And so which triples do we obtain? Well, first, for these two smaller branches, we can assume that just like recursively, we obtain triples for C1 and C2, which have like the corresponding precondition corresponding to the inhale and postconditions corresponding to the exhale. For this larger piece of code, it's a bit more interesting. We start with, in the beginning, we are in the empty state, so we just have true, and we know after the inhale, we have true, we start together with A. We also know that in the middle of the program, between the inhale and the exhale, there will be some separation logic. So we can obtain this R by deconstructing the proof in the axiomatic semantics of core IVL. And then we know that before the exhale statement, we must have R start with P1 and P2. And after the inhale, we must have R start with Q1 and Q2. Similarly, we know that before the exhale of B, we must have the ownership of B. So we can obtain this fact by deconstructing the proof of the axiomatic semantics of core IVL. And now we can look at the two parts around C0 and C3, and from this recursively obtain separation logic triples with specs corresponding to exactly what we've written here in the code. And so now that we've obtained these individual separation logic triples for C0 to C3, we can use the standard rules from CSL, in particular the frame rule and the parallel composition rule, to recombine these separation logic triples to obtain a proof in the front end separation logic for this program. And the key point I want to make here is that this is a relatively straightforward recombination of the core IVL proof by destructing and reusing the proof from the axiomatic IVL semantics. So this is how we go from the axiomatic semantics to the front end program via this recombination. And what I've shown you is the generic framework of this part of this approach, but we've also instantiated this approach for a concrete instantiation. In particular, we take a concurrent separation logic, relatively standard concurrent separation logic, and build a front end for that. I should also say all of this, both the framework and this instantiation, is done in the Isabelle proof assistant. We have then the front end translation to an instantiation of core IVL that models the Viper verifier. And here, as we briefly mentioned before, this leverages the fact that this is based on a generalization of separation algebras to what we call IDF algebras, which also allows us to model implicit dynamic frames. And then we modeled formally two backends for this for this language, for this instantiation. First one based on symbolic execution, which is a new implementation of symbolic execution in Isabelle that you can execute within Isabelle and obtain a proof there. And second, we connect this to the formalization of Viper's verification condition generation by Gaurav, as I presented this year at PLDI. And we prove the soundness of these two backends against this instantiation of core IVL to Viper, and this crucially relies on the angelic choice, because these two different backends actually have different heuristics of how they deal with, for example, wildcards. And then for the front end, and then we also connect this core IVL to the front end program by using basically by using this technique of the recombination. In particular, we also identify a specific exhale havoc inhale pattern that allows us, gives basically a straightforward encoding of the separation logic rules for the front end program into the intermediate verification language. So this is what we did in this work. There's of course a lot more to do in future work. For example, would be interesting, or like one ongoing work is looking in different state models. At the moment, the concurrent separation logic in the front end and then the core IVL language share the same state model or notion of resources. But very interesting to generalize this, and also looking into more complex frameworks or different backend verification algorithms. But this brings me to the end of my talk. I would like to thank you for your attention. If you want to learn more, you can find more information also at this link, but I'm also happy to chat more about this. I'm looking forward to your questions.
I have a somewhat naive question. I mean, this kind of verifiers have existed for ages, right? Yeah. Did people just YOLO it in the past, or were there sort of some more primitive meta theory to them?
Well, I don't know, Peter's into the room, but like, for example, for Viper, often these more automated verifiers are more sometimes more engineered with more like a practical approach for like, okay, I have this program, I want to verify it, I encode it wherever into Boogie this way, and then see how it works. And then one can then, more from the practical side, not coming from the theory side. So that is sometimes what happens with this verifiers, and this is like just an approach to thinking about, okay, how can we think formally about this? But like also other tools, for example, we talked about before briefly about like feather-wide very fast, but in the context of very fast, there people have looked at like how can very fast be formally modeled, or also in Chilean. I think like Philippa talked like last week already a bit about different approaches there, how this can be modeled. But yeah. Yeah, Amal?
Yeah, so thank you, very interesting work. So I just want to, first I think I need a clarification. At the very beginning you showed Rust and Go, but am I correct in assuming that for now, your source language is just CSL?
Yeah, so the instantiation we have for our framework is what you see here. So it's like a simple CSL with like a standard operational semantics for CSL with assumptions. Oh, yeah, it's not entirely standard. It's like a CSL based on IDF, but yeah.
So then I guess my question is, what are the challenges that you anticipate as you start to plug in different source languages with, wildly defined semantics? Maybe that's already what you're referring to when you talk about the future work challenge?
Yes. Yeah, that's a very good question. Yes. So indeed, one thing which will be very interesting. And so, like, first I should say also like Viper in particular already has like different front ends. Like, for example, it has a Rust front end, it has a Go front end, it has a Python front end, and many other different front ends. But like, yeah, like even like writing a front end on its own is like a very complex task, and then like formally modeling this is like even more complex, which is why in this work we focused like on the core of the approach. But I think, yeah, as you said, like one key thing which will be interesting to explore there is like if you look at different, like at different separation logic or different state models. In principle, like so, we have our core IVL, the instantiation, or also for Viper supports like some like the normal like separation logic PCM based instantiation. But I don't know if you, for example, it depends. Like it depends on what you want to. If you, for example, would like to encode like reasoning about unsafe Rust code, where you then want to encode something like the lifetime logic or something to this would be a lot more complex because it would be unclear whether, for example, this notion of separation algebras would be expressive enough for this, or like also just the fact that currently the front-end program logic must have the same notion of assertion as the core IVL. So there's a student currently working on lifting this and making this more flexible, but this would be something which one would need there. And just like I think, like whenever one works with like a large like programming language and complex encoding, stuff gets more tricky there. Yeah. Right. Yeah.
I was wondering about the symbolic execution. Is it would I now use this as an alternative to Viper's existing symbolic execution?
Yeah, that's a good question. So to be clear, so this is a symbolic execution which like I wrote in like whatever a month in Isabel. So it's not like comparable in sophistication to the actual symbolic execution that is implemented in Viper, and it is in some sense very naive compared to like the normal symbolic execution. For example, you have like then heuristics like state consolidation, where you look at different heap chunks and try to merge them together, or like other more complex heuristics. Which this is really just like the most simple implementation of symbolic execution I could think of. Also, to be clear, like this is still missing some of the advanced features of Viper. For example, magic wands or so on are like not covered in like the main in these backends. So it's not at the point yet where one could use it as an example for or like a replacement for the existing symbolic execution. But I think this would be an interesting direction also for future work. Can one push this version, like this foundational version in Isabel, to a point where it is comparable to the normal symbolic execution, that one maybe can use usually the normal symbolic execution, and one says, okay, now I've verified my program, I want to obtain foundational proofs in Isabel, can I use this? But this would again be like quite a bit more of engineering work and so on. Yeah.
So in the previous talk, we have seen another method to deal with multiple languages, namely this kind of hint-based approach, which you've also worked on in the past.
Yeah.
Could you compare the two, having worked on both?
Yeah, I think this is really depending on how how you set up the verification. So and how, in particular, how you set up the automation. So this work really focuses on these translational verifiers, where you say you define an intermediate verification language with like these like primitives, and then you write your verifier by saying that I take my front-end program, encode it into the intermediate verification language, and then I use the backends for this. Whereas this hint-based approach, this is really a different approach to doing the verification. There you wouldn't encode the program into some intermediate verification language, but directly write a verification algorithm using these hints. And then maybe combined with some symbolic execution, which works directly on the source language program. And I think there are different trade-offs to that. For example, one can have maybe more targeted, like with this hint-based format, one can maybe work more directly on the source program and look at the shape of the source program to apply like different automation rules. Which maybe like the shape of the source program maybe gets a bit more lost with the encoding to the IVL. But here with the IVL, one really has this nice decoupling between the front end and the back end, and one can then have like multiple front ends encode to the same IVL and then have multiple back ends.
So if you have to do refine C again, would you do it this way?
I think it would depend on the setting. Like, I don't know. Like I would. It really depends on what kind of you want to achieve with this goal. For this, like if you use something like Viper, you have already existing mature system for an IVL. If you do a verifier for scratch from your custom language and you don't have a good IVL that you can encode to, it's maybe easier to write like directly a verification tool for the language, working on the front end language.
But yet in Refined C, you or we claims that we had better automation than many prior tools. So what was the reason why that worked? And
well, I think we can have comparable automation to prior tools. I think it's really this aspect of I think this IVL approach works really well if you have a natural mapping from your front end language to the IVL semantics, where like the IVL semantics is similar to the semantics of your front end language. If you look at something like C, where you have like a weird memory model and like pointer operations and so on, which maybe don't really exist in the IVL, it's going to be like very hard to have a nice encoding in the IVL that also works well with the backend. So I think it really depends on like the IVL and the languages that you care about.
By that answer.
Yeah.
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 I was going to say, what if you can encode your memory model in the tutorial? I'm just kidding.
Yeah.
In a related effort, we get some mileage out of a sort of what would correspond here to sort of algebraically simplifying some of the assume, assert, or axiom inhales and the untitled uncertainty. Like if you phonetically quantify and then assert that it's equal to something, you can sort of simplify that away.
Yeah.
I was wondering if you could do a similar algebraic simplification of your Boogie PL style script here.
Yes, I think that is a good idea. Like, but what we tried in this approach is, to be clear, we didn't try to build a new verification algorithm, which, for example, could encode then these ideas, but we tried to model existing approaches. For example, like what like the symbolic execution or like the verification condition generation backends of Viper do, and maybe these backends I'm not super familiar with these backends. I guess they maybe do some of these simplifications internally, but in this work we didn't think about new automation algorithms, but more like how can we capture existing verification tools.
And that makes it 0 seconds left. So let's thank Michael and let's go forward.